We are the Aircraft Active Structural Health Monitoring System, Team Red. I'm Natalie Alicino, Aerospace Engineering, Project Manager and Manufacturing Engineer.
Darian Breininger, Aerospace Engineering, Design and Fluid Analysis Engineer.
Amanda Boemi, Mechanical Engineering, Team Lead and Design Engineer.
Sean Sear, Aerospace Engineering, Electrical and Test Engineer.
Gregory Phobes, Mechanical Engineering, Technical and Structural Analysis Engineer.
In the past 2 semesters, our team worked incredibly well through constant and open communication. From the beginning, we set specific roles based on our individual strengths, which helped us to easily assign tasks and actions throughout the project. We also scheduled weekly meetings, which were never missed, to help us keep each other accountable and to continuously discuss and improve our work. The established need for the system and industry and the desire to see it through motivated us to stay focused. We didn't want to let each other down, which aided in our productivity. Additionally, due to the current COVID environment, our scope was significantly simplified in order to make end results more attainable. However, that allowed us to dive deeper into specific areas such as analysis and also decrease the amount of exposure for the sake of our team members' health. The biggest lesson learned throughout this process was how to apply concepts learned in our courses, like engineering principles and analysis methods, to a physical product like the system design.
The objective of this project was to design and develop a system per end user requirements, which is primarily the military. The SHM system had to be able to detect potential structural failure, which means being able to detect stresses in the body of an aircraft which are caused by aerodynamic and gravitational loads. The manufacturing scope included a full wing assembly, which consists of an ordnance drop mechanism, a structural health monitoring system made of sensors, and a data acquisition device. The evaluation scope began with performing static, dynamic, and fluid analysis on the wing structure in order to determine the most effective sensor placement for stress detection. We will discuss this in detail in later slides. Once the system is fully manufactured and integrated, the prototype will be tested under flight conditions using a wind tunnel. During testing, the results gathered would be compared to the theoretical model obtained in analysis.
Structural fatigue is prevalent in tactical aircraft due to their advanced maneuverability, high speeds, and payload capabilities. This causes the aircraft to go through extreme loads while enduring a multitude of different environmental conditions, both on land and at sea. A structural health monitoring system drastically reduces the life cycle costs and maintenance required. Other benefits include enhanced safety and increased aircraft availability, aiding in mission readiness. Due to the COVID-19 pandemic, the overall scope of the project had to be updated. The wing was designed and manufactured for structural load testing only, and the ordnance drop mechanism was manufactured to be manual. Physical sensor installation was not possible, therefore visual testing was performed and compared to theoretical analysis to validate the system.
We also developed a testing structure, which was an aircraft wing modeled after the A-10 aircraft. The subassemblies each went through structural and functional tests individually to make sure both were properly assembled and ready for loading tests. We proceeded to perform those static loading tests by adding weights at varying locations through the wingspan and measuring the displacement. Since we were planning on using fiber optic strain sensors for our structural health monitoring system, we began procurement of the strain gauges and DAC a bit late. Before procurement of a DAC, we failed to acknowledge the need for an amplifier, which would be necessary in order to provide readable data from the strain gauges. Once we realized this mistake, we set out to manufacture our own amplifier by reaching out to experts in the MAE College and using online resources to research different supplies and methods. Unfortunately, due to circuitry complications and lack of extra components, our amplifier did not provide the necessary voltage output, which rendered it unusable for the structural health monitoring system. Since we were unable to test the sensors in this project, that is a critical path forward and the open issue. We are confident in this concept and design, but further testing has to be completed in order to take the system to its next phase. The sensor system needs to be installed onto the wing, go through the static load testing we performed to gather the electronic data, which can then be compared to both visual and theoretical results to validate our system.
We established the need for active structural health monitoring in the aviation industry, specifically the military, due to the risks and costs involved to potential structural failures and destructive and non-destructive inspections. All of the research and analysis performed set a foundation for future sensor integration and testing. The structural analysis performed established a method to determine high stress locations on a structure which are effective locations for sensor placement. Research led us in the direction of fiber optic strain sensing, which is the ideal sensor for a large structure. However, due to financial limitations, we opted to use strain gauges. The prototype presented was developed with military requirements in mind due to the maneuverability of their aircraft, which leads to high amounts of stress. Several different scenarios, such as shock, max bending, and wind tunnel simulations, were created and analyzed in order to show stresses on the prototype wing and determine strategic sensor placement. These locations were observed at high stress concentrations, as shown here. Due to the electrical complications we faced, only visual displacement data was collected for the wing, which behaved in a similar fashion as our simulated model. This shows the setup of this design was successful despite these technical complications. The ultimate goal of this design is to incorporate the system onto an operational aircraft in order to use its capabilities to increase structural health monitoring and decrease efficiency costs associated with inspections and maintenance.